we continue our discussion of SAT and its complexity. Last time we talked about NP-completeness of SAT, which is a huge result, of course, and you probably know, I'm sure you know that there are lots of other NP-complete problems out there. However, the picture of the class NP is not black and white, as was discovered by Ladner in 1975, very soon after the discovery of NP-completeness. Ladner showed that assuming P is different from NP, there will exist problems in the class NP of intermediate complexity, meaning that there will not be NP-complete, but there will not be polynomial time solvable either. So there will be something in the middle over here. But SAT and different variants of SAT seem to be very special. So we don't expect, and we can provably show that none of the natural SAT variants can be of that intermediate complexity problem. So that was discovered by Schaefer in 1978, and he said, look, there are different SAT variants that you can naturally define, and some of them we already seen earlier. There's two SAT, where you talk about satisfiability of formulas where each clause is of size 2, and we know it's in polynomial time. I mentioned that before. We also know that 3 SAT is NP-complete, but let's talk about other SAT variants that can be polynomial time. If you talk about system of linear equations, XOR SAT, you also can solve it in polynomial time using Gaussian elimination. There's a special kinds of formulas called Horn SAT, where you have clauses where each clause has at most one positive literal in it. And if you have a conjunction of such clauses, then satisfiability of such formulas is possible in polynomial time. Non-trivial algorithm, I won't go into that. And similarly, if we have so-called dual horn clauses only, these are clauses which have at most one negative literal in them, then the conjunction of such clauses is a SAT instance which you can solve in polynomial time. There are some also trivial clauses, say satisfiable by all 0 assignment or satisfiable by all 1 assignment. And these 1, 2, 3, 4, 5 classes, 1, 2, 3, 4, 5, are basically covering everything that you can think of in terms of the natural restriction on SAT and stay in polynomial time. And that was proved formally by Schaefer, who said exactly the following. He says, consider any SAT variant whose clauses are of the same type among the few types that I discussed earlier. Then if all of the clauses are of the same type, you have a polynomial time solvable SAT variant. Otherwise, meaning if you allow clauses of different types to be present in the same formula, the complexity of satisfiability jumps, you get NP-completeness. Proof idea, you consider all variants. So of course, I won't go through all the possibilities here, but I want to give you a simple proof idea for a simple case. Suppose you mix clauses of the type dual horn. Remember, dual horn clauses are those which have at most one negative literal in it. So all positive literals is fine, as long as the number of negative literals is smaller than at most 1. So say we mix dual horn clauses and with 2 clauses. Then Schaefer says that we can express NP-complete properties, NP-complete problems, and indeed we can express a well-known NP-complete problem, 3-colorability. So what is 3-colorability? To remind you, given an undirected graph, G, and you want to know if there's a coloring, which is an assignment of colors, red, green, blue, to your vertices, such that every edge is colored with 2 distinct colors on its endpoints. Okay, so can you 3-color a given graph? Well-known NP-complete problem shown early on. And it's not difficult to express this problem using the following constraints. So for every vertex, you need to say that it must be colored by one of the 3 colors. So let's introduce propositional variables R sub v, which is true or false, depending whether the vertex v is colored red, G sub v, which is true or false, depending if the vertex v colored green, and B sub v for blue. So the first constraint, which should be expressed for all possible vertices in the graph, just tells you that every vertex must be assigned one of the three colors. And notice that this clause is of size 3, but all literals in it are positive. So it's a dual horn kind of clause. Okay, so every vertex must be assigned something. The other kinds of constraint impose the restriction that you don't have monochromatic edges present. So it says that for every edge UV in your graph, it shouldn't be the case that both endpoints are same color red, or same color green, or same color blue. And this can be formally expressed as the conjunction of these clauses of with 2 shown on the slide. Okay, and if you put together all these constraints of type 1 and type 2, then you'll get a complete description of your three colorability expressed as a CNF formula. And you notice that the CNF formula has clauses of width 3, but all literals are positive. So this is dual horn, and it has a bunch of clauses of width 2. So you're mixing dual horn with clauses of width 2, and you get a formula for three colorability. So you're jumping in complexity to an NP-complete problem if you start mixing like that. Okay. So that's the idea of Schaefer's result. And so in general, not only SAT and its Boolean analogs or variants that has this property that you have black and white kind of picture, you either polynomial time solvable or you NP-complete problem. But similar dichotomy result also holds for non-Boolean SAT variants. An example of a non-Boolean SAT variant is three colorability. Non-Boolean means that you assign variables not necessarily Boolean values. So you can express three colorability as saying a vertex gets a value color 1, 2, or 3. So you can have non-Boolean alphabet to work with. And these kinds of SAT variants of non-Boolean alphabets or non-binary alphabet are also known as constraint satisfaction problems, or CSPs. And there's been a long line of work trying to prove the analog of Schaefer's result for general CSP over arbitrary constant size alphabets. And only very recently, a few years ago, by Bulatov and Zhuk, the result was proved. So now we know that dichotomy theorem also holds for non-Boolean CSPs, generalizing the result of Schaefer from the 1978. So SAT is very special. Great. Suppose you have a SAT algorithm now. What can you do with it? Well, one of the basic things you can do if you have a SAT algorithm is to find a satisfying assignment when one exists. And this is known as a search to decision reduction for satisfiability. It's a very basic thing. Let me describe it to you. You have two problems. On the right-hand side, you have SAT, which you think of as a decision version of SAT. Decision in the sense you just need to decide, given a formula, if it's satisfiable or not satisfiable. So give me one bit of information about the formula. Yes, satisfiable, or no, not satisfiable. More interesting problem, of course, is to actually get your hands on a particular satisfying assignment for a given formula phi. So you're given a formula phi in SAT search, and you want to output some, maybe lexicographically first, but doesn't matter, some assignment to the variable such that the formula relates to true under that assignment. So you want to find some satisfying assignment. Of course, if the formula is not satisfiable, this is not possible, then you have to say, no, I cannot do that. So can you solve SAT search if you know how to solve SAT? And the answer turns out to be yes, and the algorithm is pretty simple. So the result can be expressed as SAT search can be done in polynomial time with oracle access to SAT, meaning that if you give me a black box that I can query and ask SAT questions to, then given this query black box, I can answer SAT search using the following algorithm, given here in this green box on the slide, which is essentially a binary search where you use your SAT decision algorithm to divide your space of possible satisfying assignments into half, into 2 equal parts each time, and you just zero in on the satisfying assignment very quickly because you only need to repeat this log number of steps, log number of iterations, where log is log of the size of the search space. You only have 2 to the n possible candidates for satisfying assignments, so log of 2 to the n is like n iterations. And indeed, this algorithm does exactly that. It runs in n iterations. So let's just look at this pseudocode for the algorithm. So the algorithm for SAT search is the following. Given formula phi in n variables, here I'm being vague what my formula phi is. It can be a 3CNF, it can be a circuit, doesn't really matter. Similarly, what SAT decision problem I'm talking about is not particularly important here. It can be 3CNF SAT or circuit SAT. We know that they're all equivalent. If you can do one, then you can do the other via reductions. So whatever your favorite version of SAT, please pick that. Okay, so given such a phi, if phi is not satisfiable, then you output no. And this is my first oracle call to my SAT oracle in this algorithm. Okay. Otherwise, the formula phi is satisfiable. So you try searching for a satisfying assignment one bit at a time. So you want to find an assignment a1 through an to your variables, x1 through xn, starting with a1. You try the value 0 for a1, and you ask the question, if I plug in 0 for the variable x1 and look at the restricted formula where the other variables are free and x1 is replaced with a constant 0, is the new restricted formula still satisfiable? If yes, then I'll just pick and fix that 0 for the first variable. And if it's not satisfiable, but it was satisfiable, I know it should be satisfiable, and variable 0, value 0 for the first variable does not work, then it must be the case that the first variable is 1 in all possible satisfying assignments for the formulas. And so I fix my a1 to be 1 in that case and recurse. Okay, so more precisely, I have this for loop, and I try fixing the ith variable in my formula phi with a constant, starting with a 0. And if that works, this is my another SAT oracle call here. If that makes the formula satisfiable, then I'm very happy, and I freeze my variable, my value of a1 of ai to be 0. Otherwise, if this formula with 0 plugged in the ith place is not satisfiable, then I know that the variable in that position must be equal to 1. And so I freeze my ai to be equal to 1 in this case, and I continue for the next position index I. Once I'm done with this for loop, I output the found frozen values for the bits a1 through an, and it's guaranteed to be satisfying assignment based on the algorithm, which is pretty simple to see. Okay, so it's wonderful that if you have a SAT algorithm for answering decision problem questions, then you can also find object of interest to you, like satisfying assignments or free colorings in graphs and so forth. SAT is fantastic, but some properties need more than just SAT. Okay, and you can express some properties using alternating quantifiers. So let's talk about alternating quantifiers that help you to express more interesting properties than just simple SAT. First of all, SAT can be viewed as asking the following kind of questions. You have a formula phi in x1 through xn, and satisfiability is nothing but asking, is there an assignment? So you have a bunch of existential quantifiers. There exists x1, there exists x2, and so forth. There exists xn, such that phi of x1 through xn is true. You can also look at the universal quantification of your variables. And then what you're asking about is the formula phi true under all possible assignment? Which is the same as asking, is the formula phi a tautology, propositional tautology? It is true no matter which assignment you plug in. And the two problems are kind of duals of each other. you can easily see that phi is a tautology if and only if the complement, the negation of phi, that is not satisfiable. Okay, so the two problems are very related. And while SAT is a problem complete for the class NP, as we've seen, the problem tautology is complete for the class complement of NP, denoted as co-NP. Okay, and we think that SAT and tautology have different expressive power, and we don't know whether you can take a co-NP problem like tautology and put it in a class NP. So can you reduce tautology to SAT somehow? That would be like saying, is it possible that every tautology is it true that every tautology has polynomial size witnesses, polynomial size proofs? So is there a proof system that allows you to prove every tautology using polynomially short proofs only? And that would be true if it was the case that NP and co-NP are the same. And so the question whether NP is equal to co-NP has been a motivating question, and it was the initial question to motivate proof complexity, where people studied different proof systems, less general than the most general one captured by the class NP itself, and try to study the relative expressive powers of those proof systems and proving that different proof systems are not that powerful, that there are certain tautologies that cannot be proved in those proof systems, or if they can, they require quite long proofs, super polynomial or exponential size proofs. And of course, SAT and proof complexity are very much related, and we'll hear much more about proof complexity in this workshop and the bootcamp as well. One small observation here is that if NP is equal to P, then it's very easy to see that co-NP is also going to be equal to P. So co-NP in that case would be equal to P equal to NP. And so the contrapositive would say that if NP is different from co-NP, then NP is different from P. So we have a conjecture that NP is different from co-NP. This is the conjecture that people in proof complexity are trying to pursue. So what this observation says is that to prove the conjecture that NP is different from co-NP would imply that the proof that P is different from NP. So proving NP is different from co-NP is even harder than just showing that SAT is not in polynomial time. So what can you do with alternation of quantifiers? Let's look at the special case of sigma 2. It's called sigma 2 because you have two quantifiers. That's what 2 corresponds to. And sigma means that you start with existential. So you look at formulas as of the following kind. Okay, so you think of deciding the following property. So sigma 2 property is to decide the following. Given input x, you want to know if the following sigma 2 formula is true or not. If there exists a y such that for all z, w of x, y, and z is true, where w is some polynomial time computable predicate, and y's and z's, like in the case of NP, are kind of witnesses or co-witnesses, and the length of this witnesses is polynomially bounded in the length of x. So the lengths of y and z are at most polynomial in N. Let me give you a very simple example of a problem in sigma 2, circuit minimization. So the circuit minimization problem is the following intuitively. I give you a Boolean circuit of certain size, and I want to know if there exists a smaller circuit which is equivalent to mine. Okay, so is my circuit minimal, or is there a smaller circuit which does the same thing as my circuit but is of smaller size? You can express this problem as follows. So given as input the description of a circuit C, that's what these angular brackets here correspond to, in case you're wondering. You want to decide if there exists a description of a smaller circuit D of size strictly less than C, such that C and D are equivalent, which means that on all possible inputs Z, C and D assume the same value on those inputs. And so this formulation can be viewed as sigma 2 formula because you, on some input, the circuit description, you existentially guessing some polynomial long string, the description of circuit D, then you're universally guessing n-bit string Z, and then you're checking in polynomial time whether two circuits C and D assume the same value on a given input string Z. And circuit value problem, fortunately, is in polynomial time. Given a circuit, you can plug in the values for the inputs and just evaluate the circuit gate by gate. So it's very easy to do in polynomial time. And that's why the whole thing down here is in polynomial time. And so you get a sigma 2 definition for your problem. And you can generalize and you can go to k alternations in a straightforward way. And then polynomial time hierarchy is defined as any constant number of alternations. So it's a union of sigma k's for all constants k. There's also pi version, which is the complement of sigma. Okay. So very interesting result in complexity, not very difficult, but very interesting result is to say that if I have a polynomial time algorithm for SAT, then I can eliminate these quantifiers from any page formulation, any page problem that I have in mind. So in particular, if SAT is in polynomial time, then I can solve circuit minimization problem that I earlier defined, which is sigma 2 problem, in polynomial time. Okay. And the idea is kind of simple, but it's very subtle as well. So let me try to explain the proof of this theorem. So we assume that SAT is in polynomial time. Might as well assume that circuit satisfiability is in polynomial time. So let's take script A to be a polynomial time algorithm that solves circuit SAT. Good. I'm only going to show the collapse of sigma 2 to polynomial time, rather an arbitrary level of the polynomial time hierarchy to keep things simple, but this will illustrate the idea nicely. So what is sigma 2p kind of problem? It's the problem where you give an input x of length n, and you want to decide if the following formula, there exists y for all z, some polynomial time predicate w on x, y, z is true. Now we get to use our algorithm to circuit construction that we used to prove Cook-Levin's theorem. Remember, we argued that if I have a polynomial time algorithm, or more generally, algorithm running in time t, then we can efficiently construct a circuit of size roughly t, or t log t to be precise, that will be functionally equivalent to the polynomial time computation, to this algorithm Turing machine. So let's run this construction that given W spits out a circuit C, which is functionally equivalent to W on all inputs X, Y, and Z. So this reduction R sub W can be done in polynomial time. Now we can just replace W that we had in this place with functional equivalent circuit C. So now we have the problem to decide if there exists Y for all Z such that circuit C on X, Y, Z is true, is 1. And now let me just think about the internal part here as a kind of a separate problem, or rather I should also include the last part. Okay, so let me look at the inside problem here. So kind of ignoring quantification over Y and just look at X and Y both as inputs. And I want to know if for all Z, C of X, Y, Z. Okay. To make it a bit nicer, I will again take X, Y, which I'm taking now as input variables, and hardwire them into my circuit C, so that my circuit C now depends only on Z as the variables. And now when I look at this portion of my formula, what does it remind me of? It's for all Z, C of Z for some circuit C. And this is like tautology question. Okay, it's exactly circuit tautology question. I can answer SAT, so I can also answer tautology questions, as noted before. And I have the algorithm script A for answering SAT questions, so I can just plug in this algorithm to answer the tautology for circuit C sub xy. And so the existence of y such that this tautology is true is equivalent to the existence of y such that my SAT algorithm says that the circuit negation of C sub xy is not satisfiable. C is tautology if its negation is not satisfiable, as we mentioned earlier. So what happened? I had quantification over z's for all z something, and now it's gone. I've completely eliminated this quantifier over z's. And I can think now of this part after the existential quantifier over y as a polynomial time algorithm, which only depends on x and y. I call this new algorithm W prime, and the W prime will be exactly this. Okay, so W prime will take my input n, will construct the circuit C, and then we'll plug in x and y into the first two inputs of that circuit, and then we'll run the satisfiability algorithm on the resulting circuit C sub xy, actually on the negation of the circuit. And the time complexity of this new algorithm W prime is not difficult to compute. So to compute W prime, you run SAT algorithm script A. So on what input? On the input circuit C sub xy. How big is the circuit C sub xy? Well, we know it's basically the running time of our original predicate W. Or tilde is a convenient notation to use to hide this extra log factors. So time A is basically quasi-linear in time of the procedure W on input n. So what we have is that if W was in polynomial time and SAT algorithm A runs in polynomial time, the composition of two polynomial times is polynomial, and so the running time of W prime is still polynomial, but it's growing. We're not done yet, so now we have this exist polynomial time computation, which is basically NP question. We have a SAT algorithm that we want to use to answer this question. So we can do the same thing as we did by running Cook-Levin's theorem on W prime now and getting a new circuit C prime and replacing W prime of xy with C prime of xy. And then we have the question like this, which is satisfiability question for the circuit C prime with x hardwired. And now to solve this SAT question, we again use our algorithm script A, but now on the circuit C prime sub x. And if you put things together, so we now solve the problem in polynomial time, exactly what polynomial time? So what is the final running time we get for the final procedure? Well, here we apply algorithm A to the input C prime. What's the size of C prime? It's the size, it's roughly the time of the procedure W prime that C prime came from using Cook-Levin's reduction. And by plugging in what time of W prime was from earlier, we get that we can replace time W prime with time sub A of time sub W of n. So the point is that you have now composition of this SAT runtimes, which shows you that you can apply this kind of procedure only so many times, because you start with W here, which has polynomial time, and then you apply your SAT algorithm, which blows up this time more by polynomial amount, and then you apply your time algorithm to this new blown up formula, get even bigger but still polynomial time. It's still polynomial as long as you don't repeat this process more than constant number of times. Fortunately for polynomial time hierarchy, the number of quantifier alternations is only constant, so that's okay. You can handle constant k in this proof argument. And another, to me, even more interesting perhaps comment is that it's very important here to have white box access to SAT algorithm A. So you see, when you when you build this procedure that finally answers sigma 2 questions, you start by the original predicate algorithm W, and then you convert it into a circuit, and then you run the SAT algorithm on the circuit, and then you plug in the SAT algorithm into W prime, and then you run SAT algorithm on the circuit obtained from this new algorithm. And so you need to know the code of the SAT algorithm to run this procedure. It's not enough for you to have only black box access to the SAT algorithm. And that's what I mean by we need white box access to SAT algorithm A, as opposed to black box access that was enough for us to solve SAT search. To solve SAT search, black box access to SAT algorithm is enough to do it in polynomial time, but our proof does not show that polynomial time hierarchy can be solved in polynomial time with only black box oracle access to SAT. Okay. We'll come back to that in a moment.